Hi, good day everyone. Um, our discussion um, for this particular presentation is about first order ordinary differential equations again, but in this lesson, we'll talk about solving first order ODEs whose variables can be separated, and we'll demonstrate its usefulness through several examples, right? So this is our second lesson already. So let's start. In concept, many practically useful ODEs can be reduced into the form as shown. So we have g of y, or a function of y, multiplied by its first derivative, y prime, is equal to a function of x, f of x. Okay? So it says that many practically useful ODEs can be reduced to this particular form. So if we are able to reduce those ODEs to this form, then we can integrate uh, both sides of this equation with respect to x. Okay? So that the integral of g of y prime dx is equal to the integral of f of x dx plus c. So in calculus, you can recall that y prime dx is also dy. Okay? So please remember y prime dx is also equal to dy. So therefore, if we use this principle, we then have the integral of g of y dy is equal to the integral of f of x dx plus c. So if these two functions, f of x and the g of y, are continuous functions, then the integrals exist. By evaluating them, we can obtain the general solution for the given equation. Okay, so let us further explain by this example. So we are to solve y prime is equal to 1 plus y squared. So this is an ordinary differential equation, okay, which can be reduced to the form g of y prime is equal to f of x. So we know that y prime is uh, can be written to the form dy dx is equal to 1 plus y squared. Okay, so, and then rearranging these the expressions in this equation, we then have dy over 1 plus y squared is equal to dx. Okay, so our differential equations uh, differential equation is now written in the form that can be integrated in both sides. Okay, so next, what we'll do is to integrate. Okay? Once we have written our ODE into the form, we can now integrate both sides. So in this particular example, we have the integral of dy over 1 plus y squared is equal to the integral of dx plus c. So we can recall in integral calculus that the integral of dy over 1 plus y squared is equal to the arctan of y. So the integral of dx is x then plus c. Okay. So to get the value of a y, we then have to inverse, okay, the equation, so that we have the tangent of y is equal to the tangent of x plus c. Okay. So our general solution for this differential equation y prime is equal to 1 plus y squared is tangent of y is equal to the tangent of x plus a particular constant c. Okay? So another example for separable ODEs is an initial value problem. Okay? So in this case, we have uh, to illustrate a bell-shaped curve. Okay? So we are to solve y prime is equal to negative 2xy with initial value y of 0 is equal to 1.8. Okay. So again, our first step is to rewrite our ODE into the form, okay, uh, as described earlier. So at first, we have dy dx is equal to negative 2xy. So then, as a guide, we have this equation. So let us rewrite our given. Okay? So we'll come up with this particular equation. dy over y is equal to negative 2x dx. Okay? So all y's are in the right side and negative 2x on the other side. Negative 2x dx on the other side. So in this case, we are now ready to integrate both sides. So then we have the integral of dy of y over y is equal to the integral of negative 2x dx plus c. So our answer will be ln of y, or the natural logarithm of y, is equal to negative x squared plus c. Okay? So since this is an initial value problem, we wish to eliminate the value of c and replace it with a particular number or a constant. So we will use the initial value given to us, y of 0 is equal to 1.8. But then before that, we should simplify this equation first. Okay, so to simplify, we will uh, take the exponential of this equation. Therefore, we will have y is equal to c times e to the negative x squared uh, as our general equation. Okay, so this will be our general equation. Now, with this equation, we can now substitute the value of the initial value to the values of x and y, okay, to obtain our constant. So with that, y is equal to c times e to the negative x squared. Substituting the value of y or x is equal to 0 and y is equal to 1.8, we then have c, y of 0 is equal to c, y of 0 is equal to c e to the negative 0 squared is equal to 1.8. So by inspection, we know that the exponent of 0 will become 1. Therefore, we will have c is equal to 1.8. Okay? So, in this case, since we already have the value of c, we can now substitute this value to our general equation to obtain our particular solution. Right? So, our particular solution for the initial value problem y prime is equal to negative 2xy with initial value of y is equal to 1.8, the solution is, the particular solution is y is equal to 1.8 times e to the negative x squared. Alright, so this is our second example for uh, separable ODEs. Okay, our first example is an equation, ODE simple equation, and now this is an initial value problem. Okay? So if we are going to plot this particular solution, we are uh, we'll obtain this particular plot, okay, for y is equal to 1.8 e to the negative x squared. Okay, so uh, okay, application of separable ODEs. Okay, so as an example, we have an application for the heating of an office building. Okay, so suppose that in winter, the daytime temperature in a certain office building is maintained at 70 degrees Fahrenheit. The heating is shut off at 10 p.m. and turned on again at 6 a.m. On a certain day, the temperature inside the building at 2 a.m. was found to be 65 degrees Fahrenheit. The outside temperature was 50 degrees Fahrenheit at 10 p.m. And this temperature had dropped to 40 degrees Fahrenheit by 6 a.m. The question, what was the temperature inside the building when the heat was turned on at 6 a.m.? Okay. So this is a classical example of Newton's law of cooling. Okay. So what is Newton's law of cooling? So experiments show that the time rate of change of the temperature of a particular body, okay, is proportional to the difference between the temperature and the temperature of the surrounding medium. Okay, so that's it. So for our first step, we are to set up our model. Okay, so that's the very first step in this particular problem, setting up a model. Okay, so we will let a function of temperature, okay, T of T, be the temperature inside the building, and then T sub A to be our outside temperature. Okay? So this outside temperature is assumed to be constant in Newton's law. Okay? So by Newton's law, we will have this particular relationship. Okay? The different, uh, the derivative of temperature inside the building with respect to time, okay, is equal to a proportionality constant K multiplied by the difference of the temperature. Okay? The temperature of the body minus the temperature outside, okay, the building. So, so we now have a model. So this model we came up is somehow a good model, okay, based on uh, the given. So to see how good our model is, we will collect experimental data and then compare them with the calculations from the model. Okay. So for this particular example, we will use the average of known values. Okay. So our average is 45 degrees Fahrenheit, okay, given our data. Okay. So the principle behind this 45 degrees Fahrenheit is that if we cannot solve the problem has been described as if it is unsolvable, we will try to use to solve a simpler one. Okay, so since we have the unknown function for this outside temperature, so we'll replace it by the average of known values. Okay, so so this is our first assumption for this problem. So next step, we already have set up our model. We are now going to solve for the general solution. Okay. So if we can see, as we can see in our model, we have function of T, temperature, and then time at the left side of our equation. Meanwhile, at the right side, we have the temperature inside and then outside. So this is an example of separable ODEs in which we are going to reduce our given equation or differential equation into the form, into the form g of y prime is equal to f of x dx. Okay, so we now have dt, differential of temperature, over T minus 45 is equal to K dt. Okay, so this form uh, is actually a separable ODE. So what we'll do next is that we'll take the integral of both sides. Therefore, we will have ln of t minus 45 is equal to kt plus c prime. Okay, so we'll take the exponential. Therefore, we will have t minus 45 is equal to c e to the kt. As we can see here, we already have two constants. First is the c, arbitrary constant, and the proportionality constant for this particular model. Okay. Uh, and then to get the general solution, we simplify this equation so that the temperature as a function of time, okay, the temperature as a function of time is equal to 45 plus c e to the kt. Okay. So after getting the general solution, we then have to find our particular solution. Okay. So let's present our general solution. So to get our particular solution, we will use the experimental values given in the problem as our not initial but our conditions, okay, or our value problem. So we are going to eliminate two constants in this particular solution. Therefore, we need to have at least two or maybe three boundary conditions, okay, to solve for these two constants. First, the problem said that at 10 p.m. or let's say time is equal to 0, this is our initial condition. The temperature is equal to 70. Okay, so that is described in the first sentence. Therefore, if we uh, if we are to substitute these values in our general solution, we will come up with C is equal to 25. Okay. Therefore, our temperature as a function of time for our particular solution will be simplified to 45 plus 25 e to the kt. Okay. So in this case, we are left with only one constant to determine, which is the value of k. Okay. So our step number 4, we are to determine the value of k. Okay. So as our particular solution, 45 plus 25 e to the kt, we will use other conditions to solve for this k. For this instance in the problem, on a certain day, the temperature inside the building at 2 a.m. is equal to 65. Okay? So since we know that we started our time at 10 p.m., therefore 2 p.m. is already 4 hours uh, uh, after 10 p.m. So that gives us T is equal to 4. And T temperature after 4 hours is equal to 65. So this will be our condition to solve for the value of K. Okay. Let us substitute the values, uh, which will yield K is equal to negative 0.056. Okay. Therefore, our uh, particular solution, okay, without the arbitrary constants. Okay. Temperature as a function of time is equal to 45 plus 25 e to the negative 0.056 t. Okay. So as our last step in this particular problem, we are to answer the question. Okay. What was the temperature inside the building when the heat was turned on or at 6 a.m.? So with our particular solution, okay, we can now substitute another condition to our time. At 6 a.m., this will be 8 hours after 10 p.m. So therefore, we have T is equal to 8. So the question is, what is the value of temperature when the time is equal to 8 hours after 10 p.m.? So substituting the value of T to this particular solution, we will now will come up with the value of a temperature equal to 61 degrees Fahrenheit. Okay? So what we can interpret in this answer is that after 8 hours, okay, from 70 degrees Fahrenheit, the temperature dropped by 9 degrees Fahrenheit after 8 hours. So this result looks very reasonable since we know that after some time the temperature will drop according to the proportionality constant 0.056. So yeah, hence the temperature in the building dropped 9 degrees Fahrenheit, a result that looks very reasonable for this particular problem. Okay, so I think that's it. Um, this is just a graph showing the, the trend after time for the temperature to drop by 9. Okay, so that will be the end of this lesson. So to summarize, we discussed uh, a method of solving ODEs uh, by separating the variables. So at the left side, we have all the y's, or the dependent variable, the independent variable. And on the right side, we have the dependent variable. So most practicable or practically useful equations can be solved by separating its variables. Okay, so do not forget this particular method uh, because we will use this as we go along the lessons. Okay, thank you.